to DGP and welcome to Torkai. Today is December 11th, 2025, and we are super fortunate to have with us Professor Roel Vertegaal, and he's going to tell us about some of his recent research before he leaves us forever. Goodbye to Canada. This is his final hurrah, and we are so pleased to have him here. I'm not going to do a bigger introduction than that, so please, thank you for doing this.
Thanks so much, Ilona. Hi, everyone. I'm Professor Roel Vertegaal. I live in Nijmegen, in the Netherlands now, and where I run the Human Media Lab, which used to be at Queen's. And we are currently very interested in the connection between human interaction and AI. And that's because we want the human in the loop. But to answer some of the issues that arise from that, you have to think about, well, what do AI and humans have in common? And that is a way in which they think about information. And I encountered a really interesting neuroscience theory by Professor Carl Friston, who explains human behavior through a thing called surprise. That theory is called Active Inference, and so I decided to apply it to human-computer interaction. There will hopefully be a feature in Interactions magazine next year about this. There will also be a chapter in Handbook of HCI, the 4th edition, coming out about this. And we hope it can help bring people back into the loop of HCI. So interactive inference and the potential energy of actions, because of course this is the department where a lot of the Fitts Law work was done with the mouse. And so I'm going to talk a little bit about that and how we can think of surprise as an action potential for Fitts Law. So I call the greater field neuromorphic HCI. This is within the trend of neuromorphic computing, of course. The idea being that the human brain does something special that AI still doesn't do. It does things in real time. It can piecemeal learning, doesn't require huge data sets. We want to bring some of those back into the picture. So some of these ideas also apply back to AI. So applying active inference to an AI that, for example, can deal with uncertainty, which currently does not occur because everything is just flattened into a mode or a mean number, and we don't know what the actual standard deviation is, and surprise allows you to do that. So I think of interactive inference as the first theory within neuromorphic HCI. Now, why would you want this? Well, for the longest time, actually ever since the birth of mankind, we have been using essentially very reliable tools, and the whole idea of a tool was that it would do the same thing every time without fail. And essentially, you can think of a phone as a brick or like something you can cut with. It's really, the interaction style hasn't really changed. And now we're in a new era. And that means that our predictive models, which is our generative models of the world, are changing because we are now applying different interaction methods that are more akin to communicating with people than with objects. Well, what does that mean? Well, that means our generative models are going to be wrong, like this lady here who thinks that this is how you clean a display.
Right.
So the world is changing, and that means our interaction methods are changing, and that means that we need to think about generative models as user models of the world. And the thing that happens when your generative model is not according to the world, that's what's called surprise. Now I'm going to start a little earlier, though, with essentially the way in which the universe expands through the Big Bang. But the Big Bang set the conditions for what Einstein called to be the most fundamental law in physics. And it's the one law not nullified by a force, if you will. And that's the second law of thermodynamics. What it means is essentially that when a system is left as it is, it will increase its entropy. And what that means is essentially it will spread the number of combinations in which the microstates, i.e. the molecules of the system, will exist. And you see this in this fluid. If I play this, this is a very natural thing, right? The fluid always kind of like spreads. Whereas if I play the video in reverse, it doesn't look so natural anymore. It's like you're reversing time. So in fact, some physicists believe that the second law is the reason for time. That's how we experience time for sure. It's also the reason why your coffee gets cold every morning, especially on days like today. And that's because random molecules are bumping into your coffee mug and shooting away. They're not really changing the temperature of the room because there's so many air molecules in the room, but they are sucking away the energy from the coffee. It also, what you notice here is this nice crystal, and after all these random interactions, there's nothing left of the crystal. It's basically degraded. And so this idea of degradation is actually built into the universe. And there's only one thing that can actually bring it back, so counter this law, if you will, and that is work. So how does this apply to human-computer interaction? Well, users are actually continuously trying to reduce the uncertainty. That's what we call work. We report to our boss, we organize things, we run around, collect things, or we take stuff from a warehouse and deliver it, in which case the other user is collecting. So much about human-computer interaction and really any human task is about restoring order. And that's because life is based on this premise. When you have an energy source that is continuous, information starts to gather spontaneously around that energy source. You can think of a hurricane as indicating the rotation of the Earth, as indicating the temperature differential between the seawater and the higher atmosphere. This is information, and this is possibly how life started occurring, by molecules that would string together in a similar way. And that's possible if you borrow that free energy from, for example, the sun, and we call that food. You can keep your bodies organized, and this is what organisms do, and it's in fact possibly why evolution exists, is to maintain that information even across generations so that it stays. So life is really one of the few things that can counter the second law. Now that also means our brains evolved for this reason, because of course you want to predict your demise, you want to predict that predator, and you want to predict where you can get food. And if you do this wrongly, then unfortunately the second law is going to get the better of you, and this unfortunate microorganism is immediately falling apart the moment it is no longer with us. Now, how did the brain do this? Well, possibly it developed some very simple premises, like chemotaxis, for example, so gradients of smell in the water, of chemicals in the water, but also electricity signals would give you the distance, but also the change in distance if you were moving towards your target. And if you divide these, you can actually calculate the time to contact. This is a very useful number, and that number is called tau. It was first discovered by a student of Gibson, famous for his affordances, and plays a role in human-computer interaction as such. But we're going to actually build this whole thing on tau and show how it's actually fundamental, possibly, to the way our brain works. All right, so these organisms evolved ways in which tau could be translated into rapid action. Why? If there's a predator coming towards you, you need to get the hell out of there. If you're seeking food, also you need to get to the food, right? And that's the origin of Fitts' law, right? To be able to move to a target. And of course, we also have the opposite, moving away from a target. I'm going to give 2 case studies today showing how both satisfy a logarithm. So fight or flight is really what the early brain evolved in. Perhaps it's now called our limbic system, where our emotions reside. It evaluates whether or not you are right about a prediction and whether you can still get out. And it will also adjust those predictions. And if you do not get those predictions right, you experience something called surprise, which you might also consider to be an emotional feeling. So it's quite possible that there's a deep connection between surprise and emotions. Why? Limbic system was one of the first systems to evolve, directly connected to action. We don't think, we fight. Look at this. This is a staring contest at the beginning of a boxing match. What did the guy do wrong? Why did this happen? He touched, right? And you're not supposed to do that, because now you're actually not keeping that ratio of distance over velocity above a certain level. And that means danger, right? So we can think of this as a statistical distance. And the statistical distance can be used for a prediction as to, is this guy going to hit me or not? How close can I get? How fast must I move my car not to hit that tree when I'm parking? This is all tau. And perception, which is not anymore regarded as the perception we know of yesteryear, with cognitive psychologists not really being able to explain it. Perception in active inference is seen as a reconciliation between your prediction, which is this is going to happen, and your observation, which is that happens. The difference is surprise, but that surprise needs to be absorbed by the organism and then turned into either learning or action. So in this case, we think distance over velocity is going to be bigger than 1. What happened is distance over velocity is going to be smaller than 1. So, surprise, boom, amygdala says alarm, direct action, bam. Okay, so there's still quite a few people in traffic that operate this way. So, we have distance over velocity, and we could think of distance as a signal. We need to think about it as an error signal, because we're not where we want to be, right? Especially if we want to get to the target. And velocity can be seen as noise. Why? It's uncertainty in position, right? And the faster you go, the higher your uncertainty in position. And when you have a target, you need to match that uncertainty in position with the uncertainty in your target, which can be either the motion of your target or it can be the size of your target. And this codifies the probability of interaction. And what's the chances of this cat going after the dog? Well, the cat came after the dog, right? Dog jumps. This is a very clear response based on tau. I have a cat like that, and every time I turn on the light switch, it flees the kitchen. It's a stray cat, and I can't seem to tame it. But you know, in any kind of user interaction, we have the same principle, right? We can predict interaction by flicking that switch and seeing if the light turns on. So let's turn it on and wait for it. Oh, there it is. If that's less than 100%, we call an electrician, right? Yet if we deal with people, or animals or other things we can actually communicate with, then maybe we don't have that expectation. Maybe it is possible to only guess 90% right or 80% right what the other person's going to say to you or do or respond. And so that's why we need to work on this, because when we have things like ChatGPT, LLMs, agents interacting with us, in the future robots, we need to able to think about how can we predict the interaction of the other party, and we must do so in a very similar way as we do with human beings. So how does our brain achieve this? Well, let's start with this image here. What's the color of this wall?
White.
White. Any other answers?
Gray?
Gray? Yeah, that's a good one. Yeah, it's,
White.
huh?
Warm.
Warm white, yeah. Well, what we're seeing here is shadowing, right? And so our brain immediately figures out that these are two walls. There's all sorts of processing going on there, but we're not really seeing one white. What we're seeing, if you put this in Instagram and Photoshop, is a normal distribution. And what we think of white is the mean of that normal distribution, and all the gray is the error. It's the stuff that's sort of the outlier. But we use the mean to reason, and we particularly use the mean to reason about other means. How far are two normal distributions away from each other? And that's how we judge the color. The distance between these two is really what codifies surprise, and it's called relative entropy. So how can we relate this in engineering terms? Well, statistical distance can be explained in terms of two engineering principles, accuracy and precision. Accuracy is the mean proximity to the goal. I just threw a really bad throw there, but precision is the repeatability of the throw, right? So if we look at this in a more structured way, we can see that we have a low accuracy, low precision throw on the left there, a low accuracy, high precision throw if we're going for bullseye. If we're going for 21, it's not so bad. High accuracy, low precision. This is actually pretty good because on average you're hitting bullseye, but the chance of you hitting bullseye is still low. And what you really want is high accuracy, high precision. All right, so we could throw a normal distribution over this. This is a two-dimensional normal distribution, and what we see is that even though the high accuracy, low precision is centered around bullseye, the chances are low you're going to hit the bullseye. What you really want is that high accuracy, high precision. So the worst performing one is the low accuracy, low precision, and the best one is the high accuracy, high precision. So let's take those two. Now, how do humans aim in that process? Well, what you do is you take your previous throw and then you half it. And then you half it, and then you half it. And that's how you get closer to the bullseye without overshooting it. And that's called a Bayesian generative model. What you do is essentially take the normal distribution of your previous throw. If you have multiple throws, you would get a normal distribution. And the bullseye, where you can overlay a normal distribution, you multiply them. And this gives you half of the Bayes equation. And what it does is it shifts these normal distributions so that they update. And what you can then do is make your next best guess based on the previous one. You then update your throw and keep doing that until you hit the goal. And this is very much how learning works, but also how most actions are computed in human beings. So here we have the two. What we're trying to do is improve our generative model by reducing the surprise between these two normal distributions. We go from the previous aim and the goal to where the previous aim equals the goal. So, an example. I have my glasses, and I thought that I'd put them over here. And because I don't have them on, I can't see so well. So I have a little bubble, and this is a normal distribution, right? And because there's uncertainty, it's bigger, right? I look and see that it's actually over here. Now, there's two things I can do. So this is what that looks like. Normal distribution over your initial aim, and then your goal, which is tighter because it's more certain that it's there. There's an error between them. We call that the KL divergence, or the amount of surprise. We'll get back to that. It's basically the amount of non-overlap in bits, where you can talk about one normal distribution coding for the other normal distribution, and the number of bits missing is essentially this error or surprise. So there's two things we can do. You can either learn that this is where I put my glasses and I put them, there, and next time I will reach the same way, no surprise. Or I can take action and say, well, I thought my glasses were supposed to be over here. Now I'm organizing things, and now I'm actually reducing entropy by action. But they are exactly the same equation. It's just either you move the prior to the posterior, or you move the posterior to the prior. So you're reducing Bayesian surprise or relative entropy in the prediction in doing so. And what you're doing is you're making the, this is a bit tricky, but it's the distance between them is the reciprocal of the accuracy, because it gets more accurate as the distance gets smaller, right? Same is true for precision. That's the reciprocal of the noise, which is your standard deviation or variance. And so you want to match that of your goal. And you can measure how well it matches using the KL divergence. And that gives you the amount of relative information, or entropy, or surprise. It's all the same thing. This is what humans do in human-computer interaction, or actually in any task. Think about cleaning the house. When do you start with a toothbrush and then use the vacuum cleaner? You start big, you end small. Well, in Fitt's law too, you start big and you end small. So you go fast in the beginning, you go slower at the end. And so all tasks aim to reduce surprise so that the next time you're reaching for your socks, you're actually going to be able to find them. And this goes more than skin deep, because why are your socks everywhere but inside that box? It's because of the very similar random interactions that also govern the second law of thermodynamics, right? It's because you happen to drop your socks here, you happen to drop your socks there, same with the dishes, right? And so this is how disorder naturally ensues. All right, so we have precision over accuracy is a statistical distance to the goal. This is essentially tau. We can rewrite this as an error signal over a noise tolerance. Why do I say tolerance? Is because that precision in your goal is really a tolerance for the speed of update, right? If you're moving too fast on the task, what's going to happen? You're going to be sloppy and you're not going to be able to do it precise enough. If you work too precisely, you're going to take too much time to get there, right? And you won't meet the standards either. So this needs to be balanced, and therefore there's some kind of balance between the speed of the update and your noise tolerance. Now, this actually follows Shannon-Hartley's theorem, which is well known, which essentially describes how much capacity there can be in a system processing Gaussian signals, which is what normal distributions are. It's a signal plus some kind of noise stuck to it. So it's the log, and this can be any type of log, but here we chose the binary log of the signal to noise ratio. And the reason it's +1 is because it's signal plus noise divided by noise, and so that then becomes +1. Nobody ever mentions that, but so this is what the brain can do in terms of processing surprise. Now, what's different about this is that in Shannon's theorem, they talk about absolute entropy. This is relative entropy, and it's a difference because relative means that if two objects move simultaneously, then you still get this equation still holds in terms of the distance between the two objects and the speed at which they're moving. So for moving objects, it's quite important. However, the amount of surprise that is generated by the task goes up with a square. This is the same equation I just showed, signal divided by noise. It's the mean distance between the two distributions divided by the tolerance in your target distribution. And this is called the KL divergence. There's a much more complicated equation for it that involves calculating the surface of the negative logs. But if you have the same variance in both normal distributions, actually it just boils down to a squared error. And guess what? That's what we train AI on. We train AI on squared error, and this is why. Okay. So that is really surprise. But the unfortunate thing is that we have logarithmic ability to process surprise, but we have squared number of bits to process. And this is why performance and error are inextricably linked. Now, what is cool about surprise is that you don't necessarily need to know the absolute number. All you need to know is the gradient, and this also occurs in AI. We just do a gradient descent on that parabolic function. And just like you can walk down this hill and find the water down there, you could take this signal to noise ratio squared, this KL divergence, and descend it by taking a derivative. And that means I don't know where the probability, the highest probability is going to be. It's going to be at the lowest spot. So I'm just going to keep going until there's no change. And so this is really a principle of least action. We'll get to that in a sec. So this is what your brain is doing all the time. It is skiing down the surprise curve, except maybe it's not going vertically, it's just going horizontally in the case of Fitts law. But this is how we descend on the error curve. And just like with skiing, at the end, it becomes more horizontal, and you lose your speed and you reach your goal, hopefully. And there's also greater task structures in which this occurs. When you're cleaning your house, you start with a vacuum, you end with your toothbrush, not the other way around. When you drive to Toronto, you start on the freeway, then the main road, then the street, then the parking, and you do not go the same speed on the freeway as you do on the parking. So even sort of composite tasks will follow this kind of surprise curve, but each component will potentially be linear. There you go. So what this does is it connects performance directly with error. We have a capacity to process that's logarithmic on a signal to noise ratio scale, but our surprise is quadratic, and so it goes up like that. And what that means is that we have easy tasks and we have difficult tasks. And essentially anywhere where the signal to noise ratio, or tau, gets bigger than 1, errors ensue. And so we did some studies to see if this is actually the case. What this means is we have a continuum of performance and error, and in HEI we tend to express error as a percentage. We don't tend to think of it as linked to the performance in this way. And we also don't have a way to communicate between them. So this theory gives you a way to do that. In fact, it gives you a way to quantify both in terms of bits rather than time. Because part of the problem is that if you use time to quantify performance, then how do you quantify error if you use an error rate? But if you use an error rate and you use bits, then you can convert the percentage using a negative log into surprise. All right, case study 1. First, we're going to fight. So what that means is we're going to move to our goal, okay? and it's called Fitt's law. Very well known here in Toronto. But I'm showing it a little differently. What you see here is the speed of the cursor is actually shown as a normal distribution that you look at from above. And so where it's white is where it's higher, and where it's black is where it's lower. So same normal distributions as on the dartboard, but just a single line. And what we can immediately see is that if we have a goal here, which can be expressed by a normal distribution as well, it's where all the number of clicks arrive, which is your welfare distribution. And what we need to do is sort of take the speed down such that it's small enough to hit the goal without overshooting it or undershooting it. So that's really an accuracy over precision task. So it follows tau. So how does that work? Well, we can calculate a surprise curve because we know the distance and we know the size of the goal, right? And the hand is moving here, and we see that we can represent that movement as a normal distribution that gets smaller and smaller. It's a Bayesian update to the goal. And so we're actually processing bits in the process, because if you don't want to have overlap between these distributions, guess what? You have to scale them by doubling them, and this is where the bits come in. If you double something, they turn into bits, right? 2 to the power 0, 2 to the power of 1, 2 to the power of 2. And so the hand first traverses the first bit, then the second bit, and so on, until it hits the target where the bits get truncated. And so this is like bit shifting, right? Except you start with the most significant bit, and the movement ends at the least significant bit that hits the target, right? That's where the target is. So that looks like so, and like so. All right, I'm gonna show how this works in, oops. Let me just, so here you see a model of the surprise curve that would govern this. And you can see the number of bits traveled, and I can also set the size of the goal. But what we're saying is that the width of the target is really just a truncation of the number of bits processed. And guess what? That always leads to logarithmic time because we're doing a binary search. So we can start here, jump, and boom, we've hit the goal. Well, let's make the goal a little bit smaller. We start here. Okay. Let's see if we can... Oops, I have to hit reset. Sorry about that. There. Right, so that means that the surprise function would only be really related to the distance, not necessarily the width. The width is a stopping criterion. It's when you're saying you have enough uncertainty left, given the size of the target, that now you can stop. All right, let me see if I can get back to... where did it go? There. Yep. All right. So what's really cool here is that if you think of this in physics terms, then surprise is like an energy function. Okay? Energy functions in physics look very similar. And these are potential energy functions, where you are essentially using some force like gravity to convert into kinetic energy, but except using gravity, we use thoughts. And so our thought is an energy function that then governs our movement. That's pretty cool. Maybe we can do the reverse. Maybe we can actually read our minds by looking at our hand movement. That would be even cooler. Well, in physics it's called a Lagrangian. So you have a potential energy and you have a kinetic energy, and the two are always in balance, like two connected vessels. So you can convert one to the other, but the total energy always stays the same. The action is the integral over time of all these. And the principle of least action says that the change in action needs to be zero for the energy path to be optimal. So when you throw a ball through the air, that's what happens. When a photon reaches a target, that's what happens. So the whole universe is built on this principle of least action. Why wouldn't Fitt's law be? And so we've developed this potential energy function, which is essentially a signal to noise ratio, squared, with some kind of b in front of it. We can take the derivative, which then gives us an update function where we stop, so we keep sort of having this movement until we get to a position where signal equals noise, which is where it's n. right? So that is where E0 equals 0, right? When we hit the near side of our target. But there is a problem. There is a problem because our hand has momentum, it has inertia, because it has mass. The mouse also has mass. And so what you need to do is add that into the equation. It's called a heavy ball algorithm. And we can actually do an update rule that includes the heavy ball. And if we choose a dampening function, which is the stiffness here, of 0.5, we still get a binary update. But it gets a bit more messy than it would if you just use a surprise function. This yields logarithmic time. And so this is where we believe Fitts' law arises from. So what do you do to reverse this process? Well, you can reverse the Lagrangian by simply measuring the speed of the hand movement, square it, multiply it by the mass, which would be the mass of your hand, possibly your arm, and plus your mouse. And then retrieve the force field that has pushed your hand along. And then if you take the integral from 0, where your target is, all the way to the start, you will hopefully get a surprise function. This is what we're doing right now in Nijmegen in our lab. We haven't quite gotten the results yet, but they look pretty good. This is what we get in terms of velocity trajectories. And what's interesting is that these are the various widths put horizontally and the various amplitudes, so the distances put vertically. And what we see is that if we normalize for distance, we get the exact same graph for all of them. And this would imply that indeed it might be possible that what you're doing during a Fitts law task is just traversing a part of that surprise curve. And it depends on the A and W combination, which part of that surprise curve you are traversing, and that then also sets the speed, right? And the speed tends to be higher when you're further away from your target because your quadratic action is going to be steeper. So the force is the derivative of that quadratic action. So it's looking good so far. I'll get results next week, sorry. I'll let you know. I'm just going to show you the heavy ball because it's kind of cool. You can play around with it. I studied music, and we actually did this for music algorithms because it was a way to synthesize sound using physical modeling. It's very, very similar. And it's this idea of harmonic action. And that's been known that the hand makes some kind of harmonic action. And so here you see it, and I can exaggerate it a little bit. So what you actually get is a pendulum. And this is, in fact, the exact same physics of a Lagrangian pendulum. Okay? And but there is something added to it, so let me extremize a bit more. Also, this algorithm is used routinely in AI to get over local minimi. It would figure that the brain would have a model of your hand's dynamics and then play it on the surprise function in order to get the desired action. All right, so we can actually stiffen this, and now it just comes to a stop. Why is that? We introduce friction, and as the slope gets less, the friction kicks in and stops the ball, right? And that's Fitts' law, we believe. So this is potentially a way to look inside the brain without using an MRI. And therefore, it might be a way in order to think about human-agent interaction, because if we provide the agent with an update, the bigger the update is in terms of bits, maybe the bigger the surprise was, therefore, the worse the actions leading to that update were by the agent, and that means we can converge into a scenario where there's 0 updates, which in human terms is called end of conversation. Okay? So humans do this all the time. I say something, you say something. The number of things you say towards the end of conversation also follows the surprise curves, and eventually you get to least action, which is no action, which is bye-bye. And this is a little bit speculative, but you know me, I like working in the future. This may lead to a universal way of evaluating UX. Because right now we have a hodgepodge of way of evaluating, and there's really no way to compare peeling an orange with peeling an apple. Yet humans have this innate way of saying, like, well, that's a difficult task, right? And so why? Because we're not expressing it in bits. And so think of it as the principle of least action explained by taking the fastest path in a user interface from A to B. This could be over hierarchy or whatever. And then measuring for 1,000 users what their actual path is. You now have essentially a fake mean, which is the optimal path, and a real mean, and you can subtract the two. If you divide it by the standard deviation of the measured path, then you have your surprise if you square it. And so that could be a way to look at how many bits are there in a user interface. Now, this is a bit crude still, and we still have to work on this, but we did do some interesting stuff with a Wikipedia game where you have to go from one lemma in Wikipedia to another, and very often what they do is they zoom out to a page where there's more lemmas, so you get this bigger to smaller organizational step immediately. And we found that indeed, if you measured this using this kind of algorithm, you seem to be getting log linear behavior, just like Fitt's law. And the correlations, the R-squares were in the order of 0.8, so that's not bad either for just like a data set like that. So there's more data sets to explore. I'm not going to say that every task, well, I would say possibly every task has this logarithmic form, but in the ultimate task you may not see it because, for example, if you're driving on the highway, you can't go faster than 100. So you're not going to start with 1,000 kilometers an hour and end with 10. But maybe if you could, you would. If you're in a jet fighter, I don't know. All right, case study 2. Goal avoidance. So this is flight. And here we actually evaluated the theory. Now, has anyone ever wondered why this is an experiment they did in Japan with cars? And you shouldn't get a traffic jam when cars are just driving behind each other at the same speed, right? But guess what happens? A traffic jam. Why is this? It's because we're not controlling the absolute speed. We're actually controlling the relative entropy between the cars. We're doing a tau thing. We have a normal distribution, and that kind of, we want to make sure it doesn't overlap with the other car, because what does overlap mean when between two normal distributions? You're going to hit them. And so when you're tailgating or being tailgated, what is pushing you is never the car itself, right? Have you ever been hit by a car? Well, maybe a police car, but have you ever been hit by a car that pushed you? No. All they need to do is come closer within that comfort zone. Well, what is that? That is tau, right? That is that signal to noise ratio. And so we can model this like so. We have a variation in distance, very similar to Fitt's law, of a car in front of you, and we have a distance d. And the only thing that matters is the relative speed, not the absolute speed. And so these are two probability distributions, actually very similar to quantum particles and how you describe quantum particles. But we need to now say, well, we're avoiding. So this is going to be Fitt's law with a width over a distance rather than distance over the width. So we have a noise divided by signal. You could also say the noise becomes the signal, right? It's the aberration of the car in front of you that's going to determine whether you crash or not. You compare it with your action to stop that. So we did an experiment, tailgating experiment. It's really fun to do in a simulator. We had a kind of Fitt's law kind of task in the sense that we had a bar and you had to keep that on top of the bumper so that it would be the same size. But meanwhile, the car in front was behaving in a normal distributed velocity pattern, so speeding away, then stopping, and you had to stop as well. Now think about it. In a traditional cognitive science experiment, what we would do is we would measure the number of brake presses, but if you brake longer, yeah, then the number of brake presses doesn't matter. So you would measure the number, the length of the brake presses. Yeah, but if you brake more intensely, then it doesn't matter. So then you measure the intensity. It's not a good metric, right? What we did instead is we measured the KL. What did we do? We measured the velocity over the distance at the start of the trial, and once so that's when the car in front starts braking, you then had to brake yourself to get back at a certain distance. So just think of this as an inverse Fitt's law where you have to avoid, so you're going to a certain distance, and then we measure it again. We subtracted those two numbers and looked at whether that would give us a logarithm. What's also cool about this is that it doesn't really matter what you're doing in the cars. If you're not paying attention, if you're not steering right, if anything you do is wrong, your KL will be messed up. And so you don't need that eye tracker to see if you have droopy eyes or you're sleeping. It doesn't need to give you any warnings other than based on this KL. So this is the results. We got low numbers, so there may be some correlations here that are just because of the low numbers, but we saw a pretty nice pattern of a logarithmic pattern. What's cool about this is that this expresses over accuracy, precision, or signal to noise, which is the difficulty if you take the logarithm. So then it becomes bits, just like Fitt's law. And if Fitts law is just A over W. It's the same thing. But this is not time. This is amount of information in bits as well. So we're expressing how fast you can update the bits given the bits of difficulty. Okay? So bits per bit. It's a very unique measure, but it's really nice because it doesn't involve time. It's convertible to other tasks and all these other things. What we can now do is to measure the slope of this, which is the b. And because we measured it in bits, we can just plot it on the amount of information, which is the average amount of information you can process. And guess what? Shannon's theorem says beyond the average amount of information, you will start making errors. So actually the average information is your maximum information if you want to perform error-free. And guess what? You subtract the logarithm from this maximum and it peters out exactly at 1. That's not a coincidence. That's a signal-to-noise ratio of 1. And after that, you start making errors. And this is exactly what we saw. We converted the error rate using a negative log. So the percentage, negative log, you need to take complement and then negative log. And we saw a surprise function occur. But what's interesting is that the accident stayed very low up to this 1. And then all of a sudden it shot up with this quadratic function. And so this is how I believe errors relate to performance in most tasks. It also is the definition of information overload. And so what you can do is use this, which is essentially the ratio between these lines, as a metric for mental load, which means you can measure the mental load externally. And you can do it in real time while driving a car without having people fill out a questionnaire. And so that's what we did. We made some interfaces that can adapt to this. And one of the key things we did is get rid of the eye tracker. We're just gonna, it's silly because we cannot use a phone in our car, yet all our cars now have these gigantic touchscreens which you can only operate if you look at them, right? Whereas, physical knobs you can actually see in your peripheral vision and feel that you're there. So instead of taking an eye tracker and giving a warning, we represented the danger, i.e. the surprise in the task, on the screen by zooming the map based on this algorithm I just showed. So the mental load, essentially. And this was only based on tailgating, not other factors. But you could do this with other factors too. So you have to split your attention here. So first look over here. Okay, so we're almost crashing into a car coming to a stop. Now what happens when we come to a stop? We're safe again, right? And tau resolves itself, right? Because your speed goes to 0, right? So the interface should do the same thing. So let's watch that again. Here we see, as we were approaching the car, we see the zoom going up. There you go. Whoop. And then it comes back down because now you're safe again. And we then applied this, and we didn't, unfortunately, formally evaluate the ladder, but we had seen people thought that we were reading their minds. And people were able to drive the car in a straight line, braking only on the basis of the zoom function on the dashboard. So now you don't have distraction anymore because you can actually literally see the danger you're in on the dashboard. Surprise functions can also be used as generative user models, and this is a bit more tricky. But here you see a recent project that is being completed at HML. This is a pair of glasses, and what the glasses do is they track your eyes, but they also see everything, goes into a multimodal LLM, and it starts predicting what you're doing. It then creates a Markov chain, which is essentially a state machine that goes from state to state to state, and it starts learning the amount of surprise between what it thought would happen and what it actually sees, and then updates your Markov chain probabilities based on what it actually sees. And we believe this is much closer to how humans learn than what is being represented in the LLM. And we're really only using the LLM as a kind of base processor here. So I'll just play the video. It's a bit hard to parse, but what you see up here is just the prior and the posterior, and here you see what it thinks: reading screen, typing, drinking, putting down cup, drinking, reading screen, talking, reading screen, typing, etc., etc. Now it goes to erasing whiteboard, writing on the whiteboard. So it's just predicting what the next steps are going to be and then updating its functions so that it eventually can start assisting the user. And so that's Third Eye, our task predictive glasses. As you may remember, we created ECS glasses back in 2001. They were the first modern smart glasses you could talk to, and they had eye trackers too. These are now connected to a multimodal LLM. What I'm showing you now, The task prediction you're seeing here is real. The interactions are an envisionment.
Third Eye is a pair of smart glasses that can tell what the user is doing. It consists of a regular pair of glasses with prescription lenses and a worldview camera. It also has an eye tracker that can tell where the user is looking. Third Eye uses this information to determine the user's context and assist users in their activities. It does so in a completely private and secure offline fashion. Anything good here?
All high sugar snacks. You haven't had fresh fruit in a while.
Any suggestions?
Try the bananas around the corner. To your left.
How much?
50 cents per banana. Decent price here.
Apple Pay. Next, we'll see how Third Eye manages notifications while driving in difficult traffic conditions. Any new messages?
Yes, from Sarah. Meeting moved to 2:30 instead of 3. Also, Alex confirmed dinner for Alex confirmed for 7 p.m. Update your calendar with the meeting change.
Go ahead. Third Eye can also help memory-challenged individuals find items or mark when they took their medication, and many more other things. Where did I put them?
It uses a multimodal LLM to process speech and video from a scene camera to allow answers and delivery modalities to adapt to user context.
This is all real.
Here we see a camera feed during a whiteboarding session. An eye tracker records items of interest. When the user looks at a display they own,
Show me this formula in decimals from mu equals 3 and sigma equals 2.
it seamlessly switches to render answers visually. The eye tracker also records items encountered during casual daily interactions. The user can, at a later stage, query those experiences, upon which the corresponding video feed is reinterpreted.
A tree I looked at earlier today. What kind of fruits did it have? Can you show me a video about them?
It renders on the available TV. Next, we see a user entering a bookstore. He casually leafs through a travel book. The glasses register items of interest the user is fixating on. The user takes a break in a coffee shop.
Show me the place I was looking at earlier today in the travel book. The place with the llama.
Third Eye recalls what he refers to and delivers the result on his laptop.
All right. So, interactive inference. We need to design for our brain processing what it cannot predict. Our main mode of processing, and in fact, pretty much all we process, surprise. We can measure this in real time using signal-to-noise metrics very easily in a way that's UX friendly. Yes, there are more complicated formulas within the realm of active inference, but these are readily accessible for anyone. We can also base our AIs on processing of user surprise and use generative models that understand the user better by reducing surprise. This creates opportunities to manage the surprise for the user and potentially create a universal usability metric based on surprise in bits that allows us to compare apples and oranges. So in interactive inference, our brain predicts, it then observes, the subtraction of the two is a surprise, reconciliates the error as a perception action, which then leads to either updating what you know because there was an error, or acting, in which case you change the world so that the error is no longer there. That's other word for that is politics. And if you don't believe me, just focus really hard without moving your eyes on this little dot in the center and see what happens. Can anyone describe what you see?
The ball is green.
You see one single green ball, right, moving around the circle. And that's because that's the surprise in this image. Because there's actually, this is fuzzy so that you don't get very straight lines that give good contrast, so it makes it a little bit easier. But then what's happening is one of those disappears. But your brain seems to think that this rotary motion is actually a better hypothesis. And so what you see is the opposite color of pink, which is green. And so that is actually the subtraction in action. You're noticing the surprise. All right, thank you. I want to thank my students, Pepe T. Blas, Stein, and also Zaf Fountas. And if you want to know more, read the paper online. It gives all this stuff in a more mathematical form. And yeah, I'll take some questions if we have time.